So welcome to part 2 on our lecture 9 for Math 2R03. In my last part, we were talking about examples of linear maps, and we saw an example coming from calculus. And I want to show you another example coming from calculus. And this examples of this type show up kind of periodically through the course. So it's good to kind of see our first example of it. So let me walk you through the example. So what we're going to do is you can fix any two numbers that you like, a and b in R, just as long as a is less than or equal to b. And again, we're looking at the vector space of all polynomials, and we're looking at linear maps that go from the set of all polynomials to the set of all polynomials. And the way that we're going to define this map is, oh, sorry, actually, let me rephrase that. It's not exactly right. I'm going from the vector space of all polynomials to the vector space consisting of just the real numbers. And how I'm going to do that is I'm going to take my polynomial on this side and I'm going to integrate that polynomial on the interval from a to b. Okay, so and this element over here, right, is just going to be a number at the end, right? So this is an element of R because I'm doing a definite integral from a to b. So as a concrete example, suppose that I take an a to be 0 and b to 1, and I'm looking at the polynomial x squared plus t, and I'm going to stick it into this function. So it says, okay, take x squared plus x, and you integrate it from 0 to 1. So I get x cubed over 3 plus x squared over 2, and I evaluate it from 1 to 0. And my answer would be 1/3 plus 1/2, whatever that number is. And this gives me a number in the real number. It gives me a real number. Now this is actually a linear map by calculus because just like our derivative example, we're just using properties that come up from calculus. So, and why is that? Well, if we're integrating our polynomial p plus q on the interval a, b, right, we have this expression right here, but you know from calculus that you can break this integral into the integral of px on the interval a to b, and you can add it to the integral, definite integral of qx on the interval a to b, right? And so this is the same thing as t evaluated at p plus t evaluated at q. So we can think of this integration function as a map that has the additive property, and now we have to check the homogeneity property. And so if we plug in lambda times our polynomial p, the definition tells me, well, I need to evaluate this integral. Lambda is a constant, and you know from calculus that you can always pull out your constant when you're integrating. But then this thing on the inside is the same thing as plugging in p into your function t. So what we get is that t is a linear map. So these things that you were looking at in calculus, you may not have realized it at the time, but you're actually giving examples of linear maps between vector spaces. You're either giving a linear map between the set of polynomials to the set of polynomials, or you are doing a linear map from the set of polynomials to the real numbers. Okay, so that part may look new, but let me try to tie things to what you would have seen in Math 1B03. So there's a theorem here, and you can see the proof in the textbook. I'm not going to go through all the details. But what this theorem says is, let's look at the special case of our vector space V being f to the n, and our W is going to be the vector space f to the m. So we fix our field, and we're looking at the list of n tuples and m tuples. And we have a linear map going from these two. Now, this theorem says that these linear maps can only have one particular type of form, and there is a map if and only if there exists constants aij with the i's going from 1 to m and the j's going from 1 to n, such that it's taking an n tuple and you're mapping it to this m tuple, where this is the first coordinate. So we take a11 times x1 plus a12 times x2 all the way down to a1xn. That becomes my first coordinate inside of fm, and I do this all the way down to I get my last coordinate. Okay, now this may look new, but what I want to highlight, instead of giving the proof, I want to highlight that you've actually seen this before, right? Because in Math 1B03, you could look at your notes, you learned that you have a function going from Rn to Rm is a linear transformation if and only if this function right here, right, you're taking an n tuple, now I'm writing them as columns, that's what we would have seen in 1B03, is the same thing as there's some matrix out there that looks like A11 up to A1n, and then we have A21 up to A2n, all the way down to A1m up to AMN times the vector x1 through xn. Right, so we saw that we have a linear transformation if and only if there's some matrix that describes the linear transformation. But if you expand out what the right hand side is here, you're going to get A11 x1 up to A1n xn. And we go down here when we have A1m x1 up to AMN xn. And if you look at what I wrote here and what I wrote here, they're the exact same formula. Just remember that in 2R, in our textbook, we're writing everything as rows, and in Math 1B03, we wrote everything in columns. So it doesn't look like it, but there is actually a matrix hiding in the background here. So let me just put it here, that these are the same things. And so this actually holds over the complex numbers instead of just the real numbers, as we saw in Math 1B03. Okay, so hopefully this connection is helping you see what we're doing today. And then here we have an important theorem, and I'm not going to prove it, but I'll just kind of sketch out the idea, is that linear maps are determined by where bases, where a basis is sent, where a basis is sent. So let me be a little clearer about what this means. Suppose that you have a vector space and you have a basis v1 through vm of your basis, and we have n things in our basis, so we probably have an n-dimensional vector space, and then I can take any n arbitrary elements in W. Then there exists a unique linear map from V to W such that VI maps to WI. So once you know where V1 gets sent, so if you want to make a linear map, so let me rephrase this. Let's say you want to make a linear map from V to W and you know the basis. You can make that map by first picking where you want V1 to get sent. You can pick V2, you can decide where you want V2 to be sent, and so on. And that will allow you to make a linear map, and there's only going to be one linear map with that property. And here's the idea of the proof. Since V1 through Vn is a basis, you can write an arbitrary vector V as C1 times V1 plus C2 times V2 up to Cn times Vn, right? With Ci inside of your field. Every vector can be expressed uniquely in terms of your basis. And what you then do is we need to define a map T from V to W by saying, okay, I'm going to take that vector V, which I've written in terms of the basis, and I'm going to send it to C1 times W1 plus C2 times W2 up to Cn times Wn. Right, so these are the W's that I picked, and so I say V gets sent over to here. And now there's a bunch of things to check, but none of them are actually difficult to check, and they're all in the textbook. You first need to check that T has the additive property. Then you need to check that T has the homogeneity property, right? So here you're just checking that T is a linear map. So what I defined up here is a linear map, so that it belongs to the set of all functions from L to V. And then the other thing that you need to check I'll put it over here so I have more room, is that if T prime is any linear map with T prime also having the property that it sends VI to WI, then T prime V is equal to TV for all V. So basically T prime and T are the same function. Okay, we'll stop here and then I'll see you in part 3.